Hi everyone, in this video we are going to discuss about the types of error, that is alpha and beta errors, the p-value, power of the study. So we will study p-value in relation to alpha error, the power of the study, the trade-off between alpha and beta errors, how it works, and examples with some important considerations and key exam points. So let's start. What is alpha and beta error in simple terms? So alpha error is getting the statistically significant result. Statistically significant result when actually there is no effect in real. So it is like a kind of false alarm. So alpha alarm. This is a mnemonic you can remember. So alpha error means rejecting the null hypothesis. What is null hypothesis? That there is no effect. There is nothing going on. So we reject the null hypothesis. We say that study is statistically significant when actually it is not. So it is a kind of false alarm. You can remember alpha and alarm. Beta error is not getting a statistically significant result when actually there is effect in real. So it is a kind of blunder. Beta blunder, that is missing a true effect. That means failing to reject the null hypothesis when it is actually false. So coming to alpha errors, we will discuss the alpha error in detail now. When we reject null hypothesis and say that there is some real effect when nothing is going on actually, is called alpha error. So alpha error is kind of false alarm. I have said this in the previous slide as well. So let's take an example. Suppose a new drug is actually no better than a placebo. There is nothing going on, and you conclude that the drug works. That is alpha error. So this is also called type 1 error. So why, if there is nothing going on, the drug is not effective, why the data will show as statistically significant? So this can happen due to pure chance, pure luck, or random variation. It is like you go in an exam without studying and you get passed. So that is an alpha error. So it is a measure of pure chance or pure luck or random variation. So the question is, can we nullify the chance or luck completely? Can we nullify the alpha error completely? No, we cannot. Because I will take the same example again. I know that you study and you really work hard, but I am just taking an example. So suppose you have not studied at all and you go to the exam. So can you nullify the chances completely that you will not pass? No. So there is always a chance that you will pass. Similarly, in clinical research, there is always a chance to see the statistically significant data, even if there is no effect, even if both the groups are same. So we cannot nullify the random variation completely in a study. We have to accept certain level of alpha error, because alpha error measures random variation as we have discussed before. So we have to accept certain level of alpha error. In other words, there will always be chances that your data will show as statistically significant, even if there is no real effect. So we have to accept a certain level of alpha error because we cannot nullify the chances completely. So we accept to decide, we decide on the p-value. So p-value measures alpha error. So p-value, which we have discussed in the last video, is a measure of alpha error. So we decide on a p-value at which we will reject the null hypothesis. Let's say I say that I will reject the null hypothesis if my p-value comes as 5% or less than 5%. So we decide on a p-value at the start of the study. And what we are deciding, that how much alpha error I will accept, how much chances I will accept. So that is what we are saying. So as we have discussed, if we decide at the start of the study that we will reject null hypothesis at p-value less than or equal to 5%, what we are saying, I will consider my drug as effective if I get the p-value of less than 5%, even though I know that there can be 5% chances that data is showing statistically significance only due to pure luck or chance or random variation, right? So p value less than 0.5% means that I am accepting alpha error of 5%. So I will say that my study is statistically significant even though I know that there can be a risk of 5%. Okay. So alpha error in summary, it is an error where our data show as statistically significant when in fact there is no effect. It is like a false alarm, A for alpha, A for alarm. So we reject the null hypothesis when we should not, due to pure luck, chance or random variation measured by p-value, and we determine the alpha error that we are going to accept, that we are going to allow by setting the p-value in advance. We will say that we will reject the null hypothesis at less than or equal to 5%. This is usually the standard value used in clinical research, less than or equal to 5% p-value. By the way, p-value and alpha error is not the same thing. P-value measures alpha error. So we will discuss that going further. So keeping alpha error small means what? There are some implications. So if I am keeping the alpha error small, that means I need a tighter study so that I don't allow for chance. So I need higher evidentiary standards. So we will make the study design like this, that it is very tight, it does not allow for chance. So small alpha error means I will have fewer false positives, because false positive can be due to chance only. If I am getting false positive in the study, if I see that data is statistically significant, that is due to chance, that is false positive. So what alpha error measures? False positive. So small alpha error means that we will have fewer false positives. It makes easier to miss true effects. So if I have a tighter study, I am not allowing for chance, I am allowing fewer false positives. That means I will have to pay the price for it. What is the price? That I will miss the true effects. That is called beta error. It is a blunder that I am missing the true effects. So if I keep my beta error, alpha error small, I will have to increase my beta error. If the sample size is fixed, we will discuss that again. So if the sample size is fixed, then there is a trade-off between alpha error and beta error. We will discuss that in detail. So these are some points for keeping the small alpha error. Now coming to beta errors. It simply means that we fail to detect the effect in the study when in fact there was a true effect. So beta error is a blunder. So keep that mnemonic in mind. In other words, we fail to reject the null hypothesis when we should have rejected it. Example, a new drug truly works, but your trial fails to detect the benefit and you conclude that drug doesn't work. This is type 2 error. It is a blunder. So beta is linked to statistical power. We will see what the power is. So this is a mnemonic for you. So power of the clinical study is its ability to detect the effect when it is actually there. So how good your study is in detecting the effect when the effect is actually there is the power of the study. So beta error is the chances of missing an effect. So that means these two things are different, opposite. Higher the beta error, the lower the power of the study, because beta error means that inability to you miss to detect the effect, that is beta error, and power of the study is the ability of the study. So these are totally opposite things. So that means power of the study is 1 minus beta error. More the beta error, lesser the power of the study. Lesser the beta error, more the power of the study. So another mnemonic, power of the study is probability of picking up the phone when someone calls, or probability of seeing a effect when it is actually there. So if you can relate that, picking up the phone when somebody calls, or seeing the effect of the drug when the drug calls. So you can remember that if that helps. So on what factors power of the study depends? So we have already discussed higher alpha means higher power, because the more you allow the room for chance, more likely you are to detect the true effects. So more you allow the alpha error in a fixed population size, in a fixed sample size, the lesser your beta error is. Basically it is saying the same thing. So higher alpha means higher power. You are allowing more room for chance, so you can see the effects easily, even though you have some false positives. So higher alpha will give the study the power. More sample size, the more people you study, there are more chances you will see the effect. Effect size. So if your drug is very effective, that will give your study the higher power, because if the BP can be reduced by 50 mmHg, then your study is easy. Like there will be lot of power in the study, whatever the design is. So larger true differences gives the study higher power. If the drug is very effective, you are more likely to see the statistical difference basically. Then lower variability, smaller standard variations will give the study higher power. I hope this is clear. So trade-off between alpha and beta error. Now one thing you have to remember here is that trade-off is only relevant when there is a fixed sample size. There is an inherent trade-off. Trade-off means if you increase the alpha, beta will decrease. If you decrease the alpha, beta will increase. So that is called trade-off. It is like a seesaw. Seesaw, okay? Alpha, beta. But you will see this only in the fixed sample size. So in a fixed sample size, if you increase the beta, the alpha will decrease and vice versa. Why I am saying fixed sample size again and again? Just give me 1 minute. So let's see this. If there is a fixed sample size, there is a trade-off between alpha and beta error. But if you increase the sample size, by not keeping the alpha fixed, like you will not fix the error, like alpha error at the start of the study that we have discussed, both alpha and beta decreases. So we know that beta will decrease by increasing the sample size because increase in power. This is clear. But why the alpha will decrease? Because increasing the sample size means that there are less chances of random variation. You will see what is actually true. That is what increases in sample size means. So not keeping the alpha fixed, both alpha and beta decreases. Keeping alpha fixed, beta decreases to a greater magnitude. Right? Keeping alpha fixed, that I will anyways allow the room for chance. So what you are saying, I am okay to have my data as statistically significant as chance only, but I want to detect the effect of the drug if it exists. So what you are doing, you are keeping the alpha fixed and allowing for the room of chance, so that beta decreases to greater magnitude. It means we are not trying to reduce the alpha even after getting a large sample size, because we want to decrease the beta to a greater extent so that power of study can increase. So fixed sample size, there is a trade-off. Increasing sample size, if we keep the alpha fixed, both alpha and beta, if we don't keep the alpha fixed, both alpha and beta will decrease. Keeping alpha fixed, beta decreases to a greater magnitude. I hope this is clear. Now let's see some examples. So if alpha is decreased from any value to any value, 0.05 to 0.01, what happens to beta? If everything else is equal, so we are keeping the sample size fixed. Beta increases, power decreases, because we are decreasing the alpha. So beta will increase because everything else is equal, sample size is equal, so that means there is a trade-off. Right? Which error is minimized by increasing sample size? Which error is minimized by increasing sample size? Beta error decreases, alpha error stays the same if you keep alpha fixed, that we have discussed. If we don't keep alpha error fixed, this will also decrease. Right? If in a study with power 90%, what is beta? So we discuss power is equal to 1 minus beta. So beta is 0.1%. I hope this is clear. So we have some important points from the discussion. P value is not alpha. P value is the probability of observing the data, assuming H naught is true. If you have not seen my video on P value, just see it, and I explain there that P value is nothing, but it is the probability of observing the data that we are observing right now if null hypothesis is true. But what is alpha? Alpha is a chosen threshold that I will allow this error, like the room for chance, up to this level. So it is a chosen threshold to decide the significance. Alpha is not the probability of H not being true. Alpha is an error, a long run error rate, not the probability that null hypothesis is true in this study. Okay. So alpha is a threshold or a long run error. P value is a probability. P value, P probability. Ability of seeing the data if null hypothesis is true. So that is P value. Alpha error is an error, long run error, or a threshold that we decided at the start of the study. So power depends on assumed effect size. What does that mean? So if your drug is very effective, you don't need much power. If your drug is very minimally effective, you need more power in the study, in the clinical study. So power is conditional. You must specify the effect size you want to detect. If you want to detect a very small size, do you need much power? No. We need smaller power and vice versa. And statistical significance is not equal to clinical importance. So statistical significance is that your study data is showing that it is statistically significant. But it does not mean that it will be clinically important. For example, if you have mean reduction of 0.8 mmHg and the study is showing statistical significance, will the 0.8 mmHg reduction in blood pressure clinically important? No. So statistically significant does not mean clinically significant. So I have explained with more examples in my P value video. But how do we measure clinical importance? By measuring quality of life, by measuring mortality rate. All these real world examples we take, real world metrics we take. Decrease in infant mortality rate. This is clinically significant things, clinically significant metrics. So statistical significance does not equal to clinical importance. So that's it for today. I hope you have liked my video, and if so, please like, share and subscribe, and I will see you in the next video. Thanks.